Okay, so maybe we should start. So today we are very lucky and happy to welcome Uri Shalit. So Uri Shalit is an assistant professor at Israeli Institute of Technology, and his research focuses on applying machine learning methods for healthcare, and especially on working at the intersection between machine learning and causal inference. So today, I guess he will give a talk on this topic. So thank you very much.
Yeah, thank you everyone for coming, and thank you, Julie, for the invitation. So let me just say, I do quite a bit of applied work at the intersection of causality and machine learning and healthcare. I will not talk about that. If anyone's interested, please come meet me afterwards. I will talk about somewhat more theory-leaning work. Okay, so what is causality? That's a big question. And I know in France, you are strong in philosophy, and I am not. So I will not try to answer the big question, what is causality? But I will give a working definition that people who work in the field, in the applied field, try to use. So we say things like aspirin caused my headache to disappear, or the car crashed because it didn't brake in time, or the student succeeded because of the new teacher. And one way to interpret these is as follows, saying, if I had not taken aspirin, I would still have the headache, if I'm in the first example. Or if the car braked in time, it wouldn't have crashed. Or if the students remained with the old teacher, they wouldn't have succeeded. We can interpret that as a meaning of what does it mean when we say because of something. And all of these statements are counterfactuals. We're saying, if the world was different, then the outcome would be different. And counterfactuals, so we need to imagine a world where everything was the same except the cause. So everything is the same, but I didn't take my aspirin. And if everything was the same except this one thing where I didn't take my aspirin, and in that counterfactual world, I still had a headache, then I could say that aspirin caused my headache to disappear. And I mean, this is a problem because we don't have the counterfactual world. We only have our world where we live in, where I took the aspirin. So counterfactuals are often in terms of imagined intervention. I imagine something changes. I force myself not to take the aspirin. I force the old teacher to stay. And that's a way to think about them, but these are not directly observable. Okay? So in most cases, this counterfactual world is different from our world. There are very special cases where it is almost identical, or distributionally identical to the observed reality. For example, if we run a randomized control trial, so for each person, they only got one treatment or another, like in a clinical trial, but at least on the distribution, because we're randomized treatment, we could say that the distribution of the factual and counterfactual worlds is the same, and that's what allows us to infer causal effects from experiments. And that's kind of what I teach in the first class of my causal inference course. So specifically, oh, I lost it. Okay. In this talk, it will have two parts. I hope I'll manage to get through all of it. And the first, we'll talk about using machine learning ideas for causal inference. And the second, causal inference ideas for machine learning. And let's start with the first half. So specifically, there are many different interesting causal questions. I'll talk about a specific one, which is called causal effect inference. And it focuses on the effect of one specific cause. So for example, I have a medication. Maybe I have two medications. I'm debating which one is better. I just want the effect of this medication on this patient. I don't care about all the other things in the world. I want to isolate the effect of this medication. Okay. In economics, they're very preoccupied with such questions. For example, which economic policy will lower unemployment? Should we increase the minimum wage or decrease the minimum wage? That's a causal question, and we want to focus on this one thing and how will it affect this one outcome called unemployment. Okay? So it's the effect of actions on outcomes. And how can we do this? How can we answer these questions? So for example, in the medication case, we can use medical records. So I work with healthcare providers in Israel. We have data from millions of patients who receive all kinds of medication. And we can try to use those records to infer which medication is best for which patient. In the economy case, we can use past economic measurements and try to use them to infer which economic policy will lower unemployment. But of course, the problem with this is something called confounding. Okay, so confounding is a key idea in causal inference. For example, if I'm looking at medical records, let's say I'm just debating two medications, A versus B. But what if younger or wealthier or female patients tend to receive medication A versus B? And they're better, not because of the medication, but because they're younger or wealthier or anything else. Okay, maybe I see people receiving medication A do better, but it's not because of medication A, it's because of some other factor, the confounder. For example, age or wealth or gender. In economics, maybe someone increased the minimum wage 20 years ago and unemployment went down, but it wasn't because of the minimum wage, because at the same time there was just better economic situation. So confounding is the main challenge when trying to do causal inference from such data called observational. Now, specifically, I will talk about a very specific approach we developed using deep neural nets, and I'll basically summarize these three papers with my colleagues Frederick Jonsson, Nathan Callis, and David Sonntag. And I'll specify the specific problem we're interested in solving. And that's something called the conditional average treatment effect, and I'll define this in a second. So the scenario we imagine is as follows. So we have a patient coming in, and we have her medical record, and specifically we have her blood pressure, which is what we care about for this patient. And we're debating two treatments. Okay, this is the simplest non-trivial example, and we'll call them t = 0, t = 1. And we're asking 4 months in the future, which of the two futures for this patient is better? The future where she received t = 0, or the future where she received t = 1? We want to imagine these two futures and try to say which one is better for Anna. And we denote her outcome here by y0 and y1. And these two things are called potential outcomes. So imagine these two futures for Anna, but note that in our data, only one of them will be realized. She received either this or that. And maybe a year passed and she switched medication, so she's not the same patient. She's a year older. Things have changed. So really, for every single patient, we only see either this or that, either y0 or y1. And I'm saying this on a healthcare example, but this works in many other fields, such as education, economics, and so on. Okay. So these are the two potential outcomes. And if we denote the patient features by x, the quantity we're interested in is called conditional average treatment effect, and it's the expectation of y1 minus y0 conditional. And as I said, we never directly observe this quantity. We want to know this. We want to know which one is better for patients with features x, but we never directly see this. We see either y0 or y1, and the choice is not random, right? Like we said, maybe younger patients tend to get t = 1. So maybe for younger patients, we tend to have this revealed and not this revealed. And you can definitely think about this as a missing data problem where we have missingness. We want to know both, but we only get to see one at every time. And the question is, how can we estimate the state function despite these challenges? Okay. So any questions so far? Okay. So we have our potential outcomes, we have our binary treatment, and we have y is the observed outcome. So what I said, we only get to see y1 or y0. The y that we get to see, we call it just y without the parentheses, okay? And just a convenient way to write this as t times y1 plus y minus t times y0. So if a patient gets t = 1, y equals y1. If it gets t = 0, y equals y. And we have the set of confounders or measurements, which we think about as just a vector in RD. And as we said, this is the conditional average treatment effect. And a way to think about this, if we have this table, we have the historical records. Let's say we have two features for each of our patients. We observe the treatments AA, BB, and we observe the disease activity. This is what we actually see after treatment. And note that we have confounding here because patients with prior disease activity high received A, and with prior disease activity low received B. So now we're not sure what happened, if what happened is because of the prior disease activity or because of the observed treatment. And we can So note here, we had the treatment they received in the disease activity. Now I'm replacing this with both potential outcomes. Disease activity had they received A and had they received B, but we just have some of those missing. So treatment determines which of these two we get to see, and we would like to complete this table. Okay. Now, I'll give one more way to look at this. So if we have the two potential outcome functions, let's say somehow I know that this is how they look, or just this is for illustration purposes. So we have age and the two potential outcomes and mortality. So if we want mortality to be lower, so for people from this age to this age, this treatment, 1 is better than 0, but for very young people, the other treatment is better. But the problem is we don't get to see both of the populations the same. The people who get to receive t equals 0 are younger, and the people who receive t equals 1 are older. So we end up seeing this sample. Okay? For the younger patients, we see the blues. The older patients, we get to see T1, and we need to complete this. We need for this patient to know what would have happened had they been on the other curve, and that's a challenge. Okay. So how can we answer these questions? So the standard theory says that we need some assumptions, and these assumptions, unlike what we're often used to in machine learning, some of them are not testable from data. And I'm happy to talk offline. What does that mean? But let me just say that mathematically, there's something called ignorability. Patients with similar X respond similarly. And formally, the potential outcomes are independent of the treatment condition on X. That means that if I have two patients with the same X or very similar X, both their potential outcomes will be the same. They're independent of the treatment they actually receive. And overlap means that similar patients with different treatments exist. So there's no total separation of the population. It's not that only young people receive t equals 0, and only old people receive t equals 1. There is some mixing, which I can use to try to make my inference. And there are more assumptions that I will not get into. Okay? So this is the harder one. This means that basically we measured everything important. And we cannot validate this from data. So these are strong assumptions that don't always hold. But we will assume that they hold. And even then, estimation is still challenging. So we will focus on the estimation challenge, not on these assumptions. Let me skip this. Okay. So when is this an easier task? So I mentioned that if we have a clinical trial, it's easier to get at the causal effect. And if we'll think about this as a machine learning problem, so let's imagine our data set being two-dimensional. And so we have only two features, and these patients got t equals 0, these got t equal 1. And because treatment is assigned randomly, these two distributions look the same. Now, note that for each of these orange dots, we would like to see what would have happened had they been blue, right? If this patient has received t equals 1, I want to know, because the difference is the K, the conditional average treatment effect. And in an RCT, usually with high probability, someone pretty close to me will have the opposite treatment because treatment is random. Okay? So if I'm thinking about it as follows. My train set is this and the outcomes they had. I don't show the outcomes, but they have outcomes. And my test set is when I flip all the colors. And in this case, if treatment is completely randomized, the training distribution is the same as the test distribution. And then estimating K really is as easy as standard machine learning, where the train and the test are the same. And even then, we need to be a bit careful. Okay? Because we want to know the effect of T. Sorry. Where's this? Sorry. Okay. We want to know how T affects the outcome. So we want to focus our modeling power really on this one feature, very special feature T. So if we're building a neural net, we want to design an architecture that will give as much attention not in the neural net sense, but as much modeling power to the effect that T has on the outcome. Why is this important? Because often many other factors are much more important for the outcome, like the baseline health, the age, the gender would be features which are much more important for the outcome. And I care about them, but I really want to know the delta that the medication does, because I cannot change people's age or total health, but I can change the medication that they give. So for this purpose, we designed kind of our first neural network for estimating causal effects, and we do something pretty simple here. So we have this representation. We learn this representation, and then the treatment feature, we give it special a special place. It acts as a switch, and we have two trunks here for t equals 1 and for t equals 0, and we kind of learn separate functions for these two populations, but they do share a representation. So some power, statistical power, is shared between the treat and control, and some is divided. And overall, we just optimize, we just minimize some loss function, squared loss, cross entropy, any standard loss function. So the purpose of this head is to give special place to the T feature, because if I just use it as a standard neural net, it might easily get washed over. Okay. So this is kind of the first go and the first architecture. But this really would work best in an RCT situation. But in observational studies, in real data not from a trial, the train is not the same as the test. For example, treated, the reds could be younger than the blues. Okay. Now, my test set, where I switch all the colors, my test set is different from my train set. So this is a form of covariate shift or domain adaptation, and we need to be able to handle this. And note that we have no labels from the counterfactual distribution. We don't know for this patient what would have happened if we switch a label. We will never have this answer. But still, we want to be able to tell which medication is better for each of us. And so the way we address this is by learning a new representation that helps take out some of this extra variance, some of this difficulty. We learn a new representation. So, neural nets learn representations, right? And we want, under the new representation, we want the distributions to be more similar. Not identical, not the same as an RCT, and I'll explain why in a second, but we do want to push them closer together so we don't have to extrapolate as hard, right? We learned the model for the blues. Extrapolating it here is hard. As we know, neural nets especially are not very good at extrapolating. So we want to ease the burden and learn a representation where they are somewhat closer. Okay? And this is a new type of bias variance trade-off because here's one way to learn a representation which is very similar. We can map everything to the same point, right? Then the distributions are identical, but then I won't be able to say anything. So there's a trade-off here. I want to not lose too much information on the outcome, but not have to extrapolate as much as I naively would have to. Okay, so we want to make the distributions closer to some degree, okay, but not have them necessarily identical. So any questions about this idea? And sorry, the overlap assumption? We need to assume it a priori. It makes overlap better, right? It makes the distributions more similar. But again, if it's very easy to make them very similar and lose all the information. So there is a trade. That's why I call it a trade-off. We need to be careful how to trade these two off. If a priori that assumption wouldn't hold, then all bets are off. So how do we do this in the neural network context? We introduce another penalty on this representation layer, which is an integral probability metric, and I'll explain what's that in a second. But basically, it takes in two samples from the distributions of the patients who receive t equals 0 and t equals 1, and penalizes the representation if they are too far apart. And specifically, what is an IPM? It's, for those of you who are not familiar, it's a very kind of nice mathematical idea, integral probability metrics, which define metrics between two distributions. This is a general idea about the distances between distributions, which you can think of as the supermum among all the functions in some function family of the expectation of G under P0 and P1. Okay, so you take the difference, and that is an IPM. And of course, it matters which function family you take here. And a very neat result is that if you take here one Lipschitz functions as your function family, you end up with a Wasserstein distance. If you take reproducing kernel Hilbert space functions, you end up with a maximum mean discrepancy distance, which was made famous by Arthur Grayton. And we use either of those, okay? And it's what's nice, it's not obvious from this representation, but from this equation, you can optimize over them the differentiable and so on. So you can actually use them easily, quite easily in your neural net, using also some of the work from Marco Couturi about Wasserstein distances. I imagine some of you know that work. Oops. Okay, so this is an architecture, but we can prove something more general about this idea of learning representations and Kate. And we can prove a generalization. So let's just define epsilon Kate as our error here. Expected error between our estimate Kate hat and the true Kate. And as usual, we would like this to be small. But note that, again, unlike standard machine learning, we don't have any samples of Kate X. Okay, we can never actually calculate this. We never see this quantity in practice. And we want to, so we will prove, I will show now at generalization error bound. And just, we'll need two things here. I'll define epsilon ft equals 0 and epsilon ft equals 1. These are the standard supervised loss functions on the two groups t equals 0 and t equals 1. So if I'm just doing standard supervised learning on these two groups separately, this will be my generalization. And our first theorem is as follows. It says that the effect error is bounded by twice the sum of the prediction errors, plus a term which is proportional to the integral probability metric between the two treatments. Okay. And this is similar to some domain adaptation results from Scheib David, if people here are familiar with, but adapted to the causal inference. And we actually used quite a different proof technique. So what this says is that we're upper bounded by standard losses. So we want to predict well standard supervised learning on the t equals 0, t equals 1 group, but we also want the two representations, distributions to be similar to each other. And this is this kind of embodies the trade-off I was talking about. They want both of these to be small. So this is for any phi and h, not any phi of h, but there's no hypothesis class here. This is for any representation phi and function h, which are not too crazy. I mean, they need regularity conditions. And that leads to, we can derive the learnability results, a standard learnability result. And note that there's no neural nets here. There's a representation. This could be the identity function, it doesn't matter. And we have some function predicting y from x and t. Okay. Questions about this? Yeah.
So I think it relates to another question. I don't understand how you manage to bound the generalization error without anything that goes back to the hypothesis of the class, like a covering number. I mean, it's probably hiding somewhere, but
no, because okay, sorry, I should have said this is epsilon k of phi and h. Okay, for a specific hypothesis. Now we can do this. Yeah, for a fixed hypothesis. Now, if we take the supermoon, we get the standard, and we can do this. But now this you can this is an up or down for a specific hypothesis. This we can minimize with standard learning theory, and then it carries over. Okay, so
for a specific hypothesis, not what we call the generalization error, right? Because the hypothesis is a function of the same distribution over which you take the probability.
So you're saying you wouldn't call this?
I understand what the confusion was.
Yes. Okay, you're right. This is for a specific hypothesis, but this carries over immediately to the generalization. Now, this result is not optimal. We can actually make it tighter because with infinite samples under our assumption of overlap, this should actually go to 0, and this does not. So we have another version, I will not go into it, where we add another way to make them similar, not just learning a representation, but learning a weighting function. We weight the two things with respect to each other, and we can show that when we do both of these, we have kind of the theorem, the tighter theorem we would want. I do not want to go into that, but it's in our recent archive paper. Okay, and this actually goes, this goes to zero, this term goes to zero when the samples go to infinity, and we end up just with a standard supervised learning problem. So this result really is about finite samples, how to be optimal in finite samples. Okay. Any questions before I go on to our experiments? Okay. So we kind of, a new algorithm, we want to evaluate it. And the difficulty in causal inference is that there's usually no ground truth. We, like I said, we don't have the counterfactuals. So we somehow need to make them up. And this is requires either knowledge of the true outcome, so you have to synthesize at least the outcome, the two potential outcomes, or there's another way that you could use if you know the treatment assignment policy. For example, if you know how t equals 1 and t equals 0, why was it assigned to different people? For example, in a randomized control trial, I know it was just a coin flip. We could use that in a certain way. I will not go into how, but that's another way to do this. But even here, we will need to simulate something. We'll need to somehow artificially remove some units. So this is, for someone, at least I came from machine learning, this was a bit unsatisfying because we're used to just having the ground truth. But some problems are harder and you don't have ground truth, turns out. And so we are effective in both settings, but I will show just one result on something called the Icp Benchmark, introduced by Jennifer Hill in 2011. So they had, it's a real study where they studied the effects of home visits and other interventions on the health of children. And we have covariates about the children, their mothers, treatment. But what Jennifer did here, she synthesized the outcome. So it's not the true outcome, she synthesized both outcomes, so we have both potential outcomes. And overlap is not satisfied by design, but I will, it's still okay for various reasons I will not go into. And we just evaluate the mean squared error in predicting the Kate function. Again, because here we have the ground truth Kate function to compare with. And what we see is we compare BART is from Jennifer Hill, who introduced this. It's actually a very nice algorithm. It's a Bayesian random forest kind of thing, which works very well, and I highly recommend it in general for tabular data, not for images or anything like that. And we compare just with a standard neural net, then with our tar net, the one where we give T special the special place, but nothing more. And then once we introduce our kind of IPM penalty and our reweighting, so actually most of the gains are just from giving that treatment variable the special place it deserves, but we do see more gains once we add our kind of more specialized penalties for making the representations closer together. And we compared with many others. This was state of the art. Since then, like, some papers came out, which I'm not sure might have improved a bit, like 0.63 or something like that. Okay, so questions about this line of work? Okay, so since then, like, people have been starting looking more and more and using neural nets to get the causal effects, but note that this is all under the strong assumptions of the no-hidden confounding and overlap, which I think are often, the assumptions are the harder part compared with a model, but I'm happy to talk about that also. So intermediate conclusions for this line of work is machine learning is well understood where the test is equal to the train, as in the distribution of the test is the same. But once we want to learn causal effects in observational data, in real data, not just trial data, we have to go beyond. We have to say the test is in some crucial way different from the train. And in causal inference, the test is different from the train, but in a very structured way. Like, only one feature is flipped. It just happens to be the most important feature. But we can use the fact, this structured difference between the test and the train, to generate algorithms which actually could do quite well in this setting. Okay, and of course, if the assumptions are violated, things kind of start becoming worse. And these days, I'm working on implementing not specifically this, but other very similar causal inference algorithms with real patient data, trying to actually learn how to treat patients optimally. Okay, so yes.
Any insights on the number of samples you need to have good estimation with respect to the number of dimensions or features that you have?
So beyond it, there's a standard machine learning kind of number of samples. This is one way to think how it's harder. You could calculate the density ratio between the two populations, which you could do. It's not difficult because it's just P of t equals 1 conditional on x divided by P of t equals 0 conditional on x. So you can estimate that quite easily. This is just a binary variable. And the density ratio, if it's very small, you're in a bad place, basically. It means you need more samples. So your sample size, your effective sample size is smaller proportional to that ratio between the treated and control. That's one way to think about it. And as usual, the number of dimensions, it depends. Some dimensions might be not important, and that then they don't really matter. But if you just want to be very general, what you need is the standard machine learning plus this density ratio correction, which only makes things worse. It's only harder than standard machine learning. Okay. And in the RCT, it will be 1, and then you're like supervised. Okay. Any more questions? Okay. So now, so this was using machine learning. So this task is kind of classic, almost classic causal inference. People have been looking at it for a while now. And we brought kind of the tools of representation learning and neural nets to it. Now I'll look at one, maybe I'll have time for 2 cases where we took ideas from causal inference and used them for problems in machine learning. And I'll start with talking about this paper with my colleagues Gaëtan Holtz and Shai Manor from the Technion, to appear in AAAI next month. And before I start, who here roughly knows what's reinforcement learning? Okay, so most people have heard of it. I will not have time to fully explain, so my apologies for those who are not familiar with it. So again, my motivation comes from medicine, but this is more general. So if we think about doctors, they make ongoing decisions, right? Often. I mean, I talked about this one thing, just give a medication. Sometimes that's true, but for example, in intensive care, where patients are very, very sick and might die, doctors kind of act all the time. So they do something, look at the patient's blood, like their blood tests change, the breathing change, the heart rate change. The doctors respond to that, so it's kind of an ongoing cycle. And this picture kind of maps nicely to reinforcement learning, where you have an agent acting on the world, the environment now, so we talked about patient, but this is now the environment, it transitions to a new state and generates a reward. And in the patient case, the reward might be still alive, still alive, still alive, and then we're happy. So this is kind of a mapping, and where does reinforcement learning meet causal inference? So in many places, but here's a way to look at this. So for people coming from causal inference, reinforcement learning usually assumes we can intervene directly. So I was talking about medications and doctors. We as computer scientists or statisticians can't directly control what the doctors do. We just passively observe. In reinforcement learning, the algorithm plays, right? The deep learning, DeepMind's algorithm played Go many, many times, or played Atari. So you can intervene directly on your data set and see what happens in most reinforcement learning. So from a causal inference perspective, reinforcement learning is mostly about how to experiment optimally in a dynamic environment. Okay, it might be a weird characterization for people from RL, but that's a causal inference perspective. Now, looking at causal inference from the reinforcement learning perspective, so kind of flipping the picture, causal inference usually deals with cases where we cannot intervene directly, as I said, and often focuses on just a single point in time, like one medication at one point, no dynamics, without all the complications of it doing something that leads to something else that leads to something else. So again, from a reinforcement learning perspective, causal inference is mostly about what's called off-policy evaluation. So you have some policy, you can't try it, you have some other policy you want to evaluate on the policy that the doctors actually do. and often it's like very simple policies, like treat everyone. Causal inference usually does simple policies. Okay, so those are the two views, and one place where they meet. So reinforcement learning is, in a sense, causal because you intervene in the world. So where could they inform each other? So one place is if you're doing off-policy evaluation of data that comes from a dynamic environment with ongoing actions, and you possibly, if you're doing this off-policy evaluation, you do not have access to the same data as the agent. Okay? And an example would be learning from records of physicians treating patients in an ICU. So it's very dynamic, they have ongoing actions, but note that usually we will not have the same data as the doctors have. The doctors see the patient. If we're doing something, we usually have some health record, which is not the same. And causal inference teaches us a lot about what to do in these situations where you might have confounding. And some people did kind of not so good reinforcement learning on ICU data. They ignored some of the lessons of causal inference, for example, the problem of confounding. And there was kind of a paper by some of my former colleagues released kind of saying how things should be done, kind of guidelines for RL in healthcare, which I recommend for people who are interested in that. It's a short review. Okay. There is one way to talk about confounding, and especially hidden confounding, in RL. So what's hidden confounding? It's where some factors affect the action and the reward and are not observed. Hidden confounding is when our assumption that we observed everything we needed, that there's what I described above as the independence between the potential outcomes of treatment conditional on X. If that's violated, we're in a bad state. That's causal inference. People have showed this for years now. There is a way to reason about this in RL, which is using partially observable Markov decision processes, POMDP. And let me just say, what the people who got wrong here, what was the confounding they missed? Doctors, here's what they found, that doctors who treat patients aggressively, these patients tend to die. Okay? And what they recommended then is don't treat patients aggressively. And the problem with that, as I hope you understand, is why do doctors treat patients aggressively? These are the patients who are sicker. And patients who are sicker die. They don't die because they were treated aggressively, usually. They die despite the fact that they were treated aggressively. So the confounder here, the hidden confounder, was how bad was the state of the patient. So it's not like they had some data on it, but obviously not enough, because the policy they came up with using RL and this data was treat lightly. And that is pretty obviously wrong. And there were more problems with this paper, but again, they ignored the fact that they have factors which are hidden confounders that could have, that if they had known them, they would have recommended something. Okay, so we'll now say, how can you use the language of partially observable Markov decision processes to reason about hidden confounding? So just formally, shortly, I will not go deeply into this, but a POMDP is a 7-tuple where you have a finite state space. So the assumption is this state space is finite and it captures everything. Everything is Markov with respect to this. There's a finite action space, and there's something called a finite observation space. So unlike standard Markov decision processes, we don't see the finite state space. We just see the observation space, and U and Z are not the same. And there's the transition kernel and observation function, like all the functions that generate the transitions from state to state and what we observed and the rewards. These are standard reinforcement learning. The observation function is what ties U and Z together. And if we use a graph to describe this, so this is the true state of the world, U. And that's state in RL name, the causal name would be confounded. These are the actions. And R are the rewards. Let's say patient is still alive. And in causal inference, these will often be called outcomes and not rewards. Now, the doctor, pi b is this edge. The doctor sees this state, sees something, sees the patient, acts according to the state, and the reward is generated both by the state and the action. And this will be called behavior policy in reinforcement learning sometimes, because that's how the doctor behaves, and that's what we see. Okay? So again, UT is the information available to the doctor. AT is the actions like medications or procedures. outcome could be mortality, and pi b is the way doctors treat patients. And now we add to this, for the POMDP part, we add the observations. We add Z. So Z are the observations, for example, the electronic health records, which are not the same as the state. And in causal inference, sometimes these are called proxy variables. So they are proxies to the true confounder. So ideally, we would observe U, but we don't. We observe Z, and hopefully Z tells us enough about U. And that's what we'll show you. Okay, so questions about, oh, sorry, and one more thing. It's all in the next. Okay, it all changes in time. So the next state is affected by the previous state and the action, right? So we did some action, we brought the patient to a new state. Now we might do some other action and so on. Okay, and so okay, any questions about this? So this is a graph of a POMDP. This is a standard POMDP, but we think about it as a causal graph, and what we see is we get to observe data from pi b. So I will assume now. This is much more theoretical than the previous work. Infinite samples. Okay, even infinite samples, this problem is hard enough. So we observed data from pi b. The doctors act in a certain way, which induces a distribution over all the states and all the rewards. Okay, so we observe this, but we don't observe U. And now we have some evaluation policy. We want to propose a better policy. Treat lightly, for example. Okay, and the evaluation policy we will call pi e. And the evaluation policy is only a function of Z, because we do not see U. We are data scientists, computer scientists, statisticians, whatever you want. We are not yet in the hospital seeing the patient. Even if we are, we have to connect to some electronic system. So we will only get to use the Z's in our evaluation policy. And the question is, how do I evaluate the value, the policy value of our proposed policy, if I only have observations from pi b and I don't get to observe U? That's the challenge we're asking. Okay. And just for notation, we'll write p pi b superscript pi b of all kinds of things for probabilities from the observed behavior policy. So we can sample from these type of distribution, and pi e are probabilities from the targeted evaluation policy. And in general, we cannot sample from this distribution, right? Because if I treat differently, this induces a completely different distribution over everything. The only thing I know about pi e is what's a condition on Z. Okay, like what is the policy? I know what's the policy I'm proposing. Okay, so in this scenario, we observe from pi b. We want to evaluate something pi e of zt. We do not see U. We cannot. It's impossible. It's very easy to prove that this is impossible, even with infinite samples. Okay, that you have it's not identified. Okay. And as we said, this example of ICU doctors treating sicker patients more aggressively is we saw that in the real world where people got this wrong. Okay. And it's impossible even if you condition on the entire observable history. And again, it's very easy to show these impossibility results. And the problem is you have hidden confounding. You have these UTs, which could be the true causes of things, and because you don't see them, you might miss the true problem that the patient has. And hidden confounding by UT is people in causal inference have been thinking about for a while, but this is even harder because of the dynamics. So you have all these ongoing correlations between the confounder and the action of the confounder, which makes everything even harder. So what we try to give is saying, okay, this is impossible. We have to make some assumptions. And we give, to the best of our knowledge, the first set of non-trivial assumptions. A trivial assumption would be Z equals to U. Then we're fine. So we give something less trivial than that allows us to evaluate a policy pi e, even if we only see it from pi b. Okay, given infinite samples. Okay, as I said, this is still on the theory side. And what we do is we use a nice idea that came out from the causal inference literature, but let me just say it here. We need to make the following assumptions. We need to assume that ZT are discrete variables. So that's one categorical variable, okay, with as many categories as U. Okay? This is an untestable assumption because we don't see U. Now in causal inference, there's almost always untestable assumptions. So if someone talks about causal inference but doesn't tell you what's the untestable assumption, they're hiding it somewhere, usually. So you should press them on So here our untestable from data assumption is that Z is discrete with at least as many categories as U. Okay. Now we define the following matrix, which is probability under pi b that ZT has value I and ZT minus 1 has value J, and the action is. Okay, so these are matrices. We could estimate these from data, right? Because these are all observables. And turns out, here's our result. If these matrices are invertible, then we can, and we can evaluate the value of a proposed policy pi e given observation. Okay? So this assumption is testable. We can just evaluate these matrices and see if they're invertible. This is not testable. Under both assumptions, we can evaluate a proposed policy pi e. Like I said, I think as far as we know, this is the first off-policy result for POMDPs. Usually people from RL, again, to the best of our knowledge, didn't really think about off-policy evaluation in a POMDP, but this is an interesting problem as we saw from the ICU example. And just very roughly, the intuition is that the future and past, these two are conditionally independent condition on U, and they act as proxies for these U. So we have two independent proxies, and the fact we need two of them, the two is important here. And given two independent proxies and the invertibility condition, we don't directly recover U, but we can recover pi e. Okay, so it's not like we discover what was the hidden confounder, but we don't actually need that. We can directly evaluate pi. Okay, and the invertibility condition is like the invertible matrices are kind of full measure in the set of these conditional probability tables, so it's not such a crazy assumption. Any questions about this? So, no, yeah. It doesn't, okay, here's what people usually ask. Why not add something to Z? Just artificially. We're not saying that they're finite dimension. We're saying that they're categorical. So if I add another category here and it's empty, these will not be invertible. If it's not empty, I change the distribution of Z. So there's no easy way around that. Okay? I can't just simply append something. That will not work together with the second assumption. And basically it means that there's at least potential for Z to have the information in U. It might be all mixed up, right? Let's say U is binary and Z is binary, but it's a mixture. Sorry? Well, not necessarily. I don't even have names. I don't know what are the variables U. Let's say the variables U have 3, could take 0, 1, or 2, and the variables in Z could be from 0 to 10. And I just need, let's say they don't really need, if they have more, I need this not to be rank deficient, this conditional probability matrix. It's not like two categories merge into one thing. Okay, I need them to be separate, but I don't need to actually identify the U's. I don't even need to know what they are. I just need to assume they're not too rich. If U has many possible situations and Z has a few, then I cannot discriminate them, and that's easy to prove an impossibility result on that in that case. I wouldn't think about it as a vector space because it's really just discrete. Oh, sorry. So where is this? So really, let's say Z could just take two values, right? So if you replace here, imagine U is binary and Z is binary. Okay, then we don't say this, but it's this invertibility implies that the matrix conditional probability table of Z conditional on U, it's a 2x2 table, and that table is rank 2. Okay, if everything is binary. So it's not really a vector, I mean, you could call it a vector space, but it's not really a vector space, it's just conditional probability tables, or of Z and U, or Z and the previous Z. Okay, so how do we do this? I will not go into it, but to actually do this, we need to define a very nasty set of matrices. So this matrix is again a joint probability matrix. Now I take the M matrix and I invert it and I multiply it by this. Then I have something I won't even explain. Then I multiply all these inverse matrices times this, and so on and so forth. I end up with something which is terrible if you think about it statistically, because I needed to estimate all these empty matrices, all these ZT conditional ZT minus 1, invert them and multiply them all together. Okay, so in infinite samples this is nice. In finite samples this is practically useless unless the sizes are very small, unless like everything is 2 by 2 and I have like 2 or 3 time sequences. Otherwise, from real data, estimating all these matrices and their inverses will be really hard. Okay, we do have some improvement. We have something called decoupled POMDP, which is not as bad, but is still not. I would not use it for real data. Okay. So the current challenge, so this is a theoretical result. The current challenge is to scale this to realistic. It doesn't have to be health, but something that works in real data. So we need to kind of understand how can we replace these inverse matrices with something that will actually, we can estimate from real data, even if it's not theoretically kind of 100% proof, sound proof, it's something we can work. Okay, but at least we have something in hand before we had nothing. Okay, so how much time do I have? Like 5 minutes, 3 minutes. Okay. Questions about this POMDP thing? Okay. So I will, let's see. I will tell you about the problem without telling you the solution. This is, again, we're using here in this work, we're using a causal idea to solve a machine learning problem. So it's not causal inference, but it's causal inspired. So we all know machine learning had amazing successes on all these data sets, on classification and on prediction, and I think that got a lot of people excited about machine learning. But there's also problems. So who here has seen the easy cows? Just Judy. Okay. So you should know about this. So this is taking a picture of a cow and giving it to a state-of-the-art image recognition algorithm. And that algorithm has never seen this cow, so it's a true test set example. And it says cow with very high, like cow, cattle, mammal, grass, very successful. This is like one of the headline successes of machine learning. But now to this same service, you give this cow, okay? And it says there's no person, a beach, water, sand, sea, but there's no cow in this list, okay? So it doesn't say wrong things. There is no person here, there's a beach here, but it misses the cow. And any guesses why it misses the cow? It's the background, right? It has to be.
It's a cow in an unusual situation.
Exactly, it's a cow. Right, it's a cow in an unusual situation. Now, we could be pretty sure that if the training set had many cows on beaches, it would not be a problem, right? But it doesn't have. And by the way, this is a real picture from India. Okay, India cows are in places that you wouldn't expect, maybe in Europe or North America. But the thing is, we as humans have no problem recognizing this. Even more, I could take a cow, put it in outer space. You've never seen a cow in outer space. You'll have no problem recognizing it as a cow. So these algorithms fail in ways that we do not expect them to fail, and they do not generalize in certain situations. Here's another example. These two sports players, okay, are classified as a basketball, not a basketball player, as a basketball. And this is classified as a ping pong ball, okay? And again, these are heavy biases in the data set, but again, these are mistakes that no human will ever make. Okay, so these are all cases where the test is different from the train. We've seen this before, but we know humans can succeed here. We know these are not hard problems for humans, but turns out these are hard for machines. So the question is, how do we design models which are robust to a priori unknown changes in the test distribution? Okay, so have this source, you have a set of possible targets. Of course, it can be too big, but you want a reasonable set of changes to be robust against. So how do you do that? That's an interesting question, and we deal with, a tiny part of it in this work, which uses ideas from causal inference, but I will not have time to go into this. But I think this is a very interesting problem, and a lot of people are thinking about it in many different contexts, not just in images and not just using causality. But I want you to at least know that this problem exists, and it's worth thinking about because it has implications not just for robustness, but also for fairness and other things that we care about. Okay. Okay. Oh, of course, we're much better. Obviously, doing something. Okay, so we saw two things. We saw how to use machine learning for a classic or almost classic causal inference problem, learning the individual level treatment. We have a neural net architecture and some theory about learning these types of functions, the Kate function, the treatment effect for some high dimensional x. Then we saw how POMDPs can encode this idea of confounding, including Kate confounding, which is crucial when trying to learn dynamic policies from observational data, and gave an identification result, which is currently only useful with infinite data. We mentioned the problem of learning robust models, and I'm going to talk about the solution later. And I just want to thank my collaborators, Fredrik Johansson, David Sontag, Nathan Callis, Guy Tenholtz, Shai Manor, and Daniel Greenfeld. And I want to thank you for your time and attention. So thank you very much.
There's certain relation between what you would be speaking in the end, and you didn't have time, and the general problem of dealing with systematics in measurement, systematic error. But the big difference is that it seems that you are very focused on at least categorical variables, and systematics is typically about continuous variables. So I would be happy to discuss that.
That's an interesting, I think, so the question is, what is this superset? Like, what changes am I allowing? And you're saying the changes are that the x's I see are not necessarily the same x's because I might have errors on them. There is, for example, there's a very simple case where you could show that ridge regression is actually robust against changes, against measurement error, Gaussian measurement error in variables. You can show that ridge regression does that, like standard ridge regression. More generally, I don't know, but that's an interesting question. I haven't thought about that. But I care about continuous variables, not just categories.
Sorry, going back to the first part, I was surprised by your results when you show that the method performs part, even when you don't tie the two distributions, the representations to be essentially mixed. Because, well, on many things that you have tried, part was actually as good as you could. So,
yeah.
Is it because it's a very large sample problem, or?
It's not a very large sample problem. We were also expecting BART to do better because it's a good method. Yeah. It did better than many other things. It did better than, for example, regressing separately both populations and so on. But that's the result we got. I generally recommend BART for these types of problems because it's very easy to use compared to a neural net. Right?
In that case, how did you generate exactly the representations, the file?
We had not a very deep neural net. We had like 2 layers, ReLU. I forgot the exact numbers, but they're in the. But it was 2 layers and then 2 layers after the representation per head. Very simple because the sample size was small.
And so, any hints on the good way to build such representations in general? If I had to do that now, how should I do that?
so okay, I'll be honest, because I now do this on real healthcare data, and I chose not to use neural nets. I experimented with neural nets. I think neural nets for tabular data, the kind of healthcare records, not for image data or something. For tabular, we have not found neural nets to generally be better. We tried neural nets on our data. They did not do better, and they're more sensitive. So for health record data, I do not recommend. However, if you have images, you should definitely be using convolutional nets and so on. Yeah.
I don't know if you have any plan to do some extension with time series.
We were thinking about that. We don't have any current plans to do that. I mean, in time series, things become more complicated because you have this feedback. Even in the easier case, when you measure everything, you have this feedback loop. No, we have another algorithm for time series data, the deep Markov model, that doesn't do the correction for it. Like, it doesn't bring things together. It does. It is possible there to give special place to the treatment, which, as we saw, was maybe the more important, the bigger gain. And it's a variation autoencoder type thing.
I guess we can thank you again.
Thank you.